Welcome to this session on modeling and simulation of an AUV. In this session, we'll take a look at how we can model AUV dynamics, then simulate the environmental forces and the sensors. So we can see here the disturbance from one dimension is propagating into another direction. So this is X, Y, and Z dimension. A disturbance in Z direction is propagating in Y and Z direction too. It's because the dynamics of the system are coupled. We'll take a look at how we can model this, how we can simulate it in an environment, and take a look at how we can simulate the sensors and in the real world scenario. So this is the trajectory that we give to our AUV to follow. Now, we'll cover some basics of an autonomous underwater vehicle. We'll take a look at how we can model the vehicle dynamics and the environment, okay, considering all the forces and moment. Then we'll dive into how we can do it in Simulink. Okay? And lastly, we'll take a look at some control laws. Now, an AUV is a computer control machine. So we basically deploy it underwater and it has to perform certain tasks. And the system that are of interest to us are like the sensor system, controller, and the propulsion system. So the sensor system is basically, it basically tells for the AUV what is in the environment. Okay, it's basically like a perception system. It's how the robot perceives the environment. And when you have the perception of your environment, you plan certain actions, give it to your controller, then controller executes all those decisions in real world using propulsion by commanding propulsion systems. Now, the dynamics of an AUV are very similar to a flying object and rotor or aircraft. The reason because both lift and drag forces are common in both the cases. These forces originate because of the fluid surrounding the AUV, the geometry of the AUV, and the dynamics of the AUV. So the main forces involved in AUV are your thrust force, lift force, drag force, weight, and buoyancy. Buoyancy force is because of the fluid density around it. And since we are considering it as a rigid body, not a rigid as a rigid body, these forces do induce moment. These forces do induce moment. Now let's take a look at like the forces along vertical and horizontal axis. In the horizontal axis, you have propulsion force and drag force. So propulsion force come from your thrusters and drag force come from the surrounding fluid, surrounding environment. So if you sum up the drag and propulsion forces, you get the net force along the horizontal direction. Similarly, along the vertical direction, you have your weight. You have your weight from your AUV and buoyancy and lift force. So the buoyancy force is exerted by the fluid on the AUV, and the lift force is generated because of the motion of the AUV, the geometry, and the fluid surrounding it. Now, AUV, so for an AUV, you have 6 degrees of freedom. So let's take a look at let's take a look at rotational degrees of freedom. First one we have is a yaw, which is along z-axis, then roll, which is along x-axis, and pitch, that is along y-axis. Similarly, we have translational degrees of freedom. So along x-axis, we have surge. Along y-axis, so along z-axis, we have heave, and along y-axis, we have sway. So we'll be using blocks from Aerospace Blockset. So the first block that we'll use is a 6 degree of freedom block. So basically what you do is you feed in your forces and moments, and the block basically computes your quantities of interest like velocity, position, angles, all with the, and you don't need to compute all the complex mathematical equations. The block selects the solvers and the initial guesses for you. Similarly, we'll be using rotation and coordinate transformation blocks. The reason why we are using this is because we have reference frame and body frame. Okay, and to maintain the relationship between them, you have certain matrices and certain computations which you have to perform. By using these blocks, you get rid of all those inner steps which you have to do. And we'll be using IMU sensor model to simulate our IMU sensor. So using this block, you can simulate your sensors using real life conditions. Like you can add Gaussian noise or colored noise. You can even specify the parameters of accelerometer and gyroscopes. So our model, our vehicle dynamics and environment modeling will look something will be something along this path. So first one we have is we have a reference position and reference velocity. We feed it to a controller. Then controller gives out certain inputs, and we have a plant model over here. So we'll discuss in next slide in detail about the plant model. So this controller input goes to the vehicle model. Environmental forces act on it. We solve the equations and we get an output. Now this output is taken by measured by a sensor data and the state estimator. So and it's then fed back to controller. Sometimes it's not possible to measure certain parameters, or if you have some like a lot of noisy sensors, it becomes really hard. It becomes really hard to estimate the state of your system. So in that case, you use a state estimator. Now to now in the plant model, we have two parts. First one is your vehicle model, and second is your environmental model. So the vehicle model is basically your forces and moments generated by your vehicle, by your AUV. And in environmental model, you have hydrodynamic forces and hydrostatic forces and corresponding moments generated by that. So hydrodynamic forces are the forces that change with respect to the motion of the AUV. It's like lift and drag. Okay. And hydrostatic forces, they are forces that remain fairly constant with the motion of your AUV. So like weight and buoyancy, they won't change. Let's take a look at let's take a quick look at modeling workflow. So we first estimate the forces, okay, by using dynamic equations. Then we construct a model. We perform open loop testing. Open loop testing means, let's say you have your model of an AUV. You give it an X command and you see the response of the system, okay. And depending upon that response, you do your controller development. Now let's take a quick look at Simulink demonstration. Uh, all the equations that I've used from this paper called Submarine Dynamic Modeling, and I have pinned down a link here. So we have modeled our AUV as a rectangular rigid body, okay, and it has 5 sensors. Oh, sorry, 5 actuators. Let's take a look at plant and environment model. So as mentioned, we have two kind of forces and moment: the vehicle forces and the environmental forces. So once when you have your thrust commands coming from your controller, okay, what you do is like you convert them into PWM signals. So you have your thrust command in X, Y, and Z direction. So you convert them into PWM signals, and again, once you have to after you convert them into PWM signal, you have to again convert them into thrust signal for the thruster configuration. The reason why we do it is because the controller gives us the forces required in X, Y, and Z direction, but as seen in the figure here, yeah, we have five thrusters. So we have to calculate the amount of force required for each thruster. Okay, and the way we do it is by uh, system. The way we do it is by system identification. So when we have PWM signals, we need a system model which we find by system identification. So system identification is a process of determining system models from your data. We'll be covering more about it in our upcoming webinar. So once you have your thrust forces, okay, then you calculate the moments. Yeah, and once you have your so to calculate moments, you basically take the cross product. Yeah, you take the cross product. Uh, once you have your propulsion forces, okay, then let's take a look at environmental forces. So as mentioned previously, there are two kind of environmental forces. First one is your hydrodynamic force, and the second one is your hydrostatic force. Hydrostatic forces are constant. So uh, buoyancy and weight, they are constant. So here you can specify the density of water, density of the environment, or so let's say you have seawater or like normal river water, you can specify the density accordingly. Volume of your submarine, the mass of your submarine, and the distance between center of gravity and center of buoyancy. So for this model, the center of gravity and center of buoyancy is the same. Okay? And this is how we have computed the buoyancy and drag. So once you have your buoyancy and weight, okay, these forces do not change as your AUV moves. Let's take a look at how do we calculate hydrodynamic forces. So hydrodynamic forces basically consist of the lift and drag forces. These forces change with respect to your motion of your AUV and angle of attack. So you can model it in two ways. First one is a high fidelity modeling, which is like more accurate, and the second one is low fidelity modeling, which is little bit which is less accurate. Now, let's say you're doing some complex tasks like control development. In that case, you need to have high fidelity model. So because so the difference between basic and low and high fidelity model is, in low fidelity models we have assumed lift and drag to be constant. Okay, while in high fidelity model, the lift and drag coefficient, they change with respect to angle of attacks. And when you are doing control law development, you want your environment forces to be accurate in order to generate a to generate a accurate control law and to do proper testings. Similarly, if you're doing some certain tasks, then you might not need like a high fidelity simulation, as it will only add to the complexity of your computation. So in that case, you can go for low fidelity simulations. So here we have specified the drag coefficient to be constant. Okay. Similarly, for lift, we have specified the lift coefficient to be constant. Now, to model now if you want like a accurate model or a high fidelity model, then one way is to like test your AUV in a in a water tunnel, get the input output data, fit the curve on it, and find out the relationship for the drag coefficient. So here, uh, as I've mentioned you the reference from, so here according to the experimentation, the drag coefficient is calculated to be this. Okay, I have linked the paper in the presentation. Now, once you have your like, this drag coefficient is computed from your input and output data. So once you have input output data, you fit the curve, and that's how you get this equation. Similarly for lift coefficient, you calculate it using the same way. Okay, you have your data, you fit the curve, and you find the equations. Now, once you have both of your environment forces and propulsion forces, you combine them, okay, and you put into a dynamic solver. So this is the 6 degree of freedom solver that I talked about. You feed in your forces and moments, and it gives you your quantities of interest: velocity, position, angles. And once you have all these quantities, you use the rotation and the translational walk to maintain the relationship between the reference frames and your body frame. Now, once you have your plant and environment model ready, we move on to sensor data and state estimation part. So here we have two parts: system with noise and system without noise. So system with noise is the scenario where your sensors are perfect, okay, and you're measuring exactly the same output. So here in this case, there's no noise in the system. In this case, there is no noise in the system, and the the signal which are measuring position and velocity are exactly the same. They are the exact same signals. Now, but in real life, no sensor is perfect. There will always be a noise in the sensor because of thermal agitation or some physical phenomena. So to model this, to model an IMU, we use an IMU sensor block. Okay, and once I go into it, you can specify your IMU location here. Here my IMU is my IMU location is at the center of gravity. Similarly, you can specify acceleration parameters, the gyroscopic parameters, and the noise. So depending upon your depending upon your manufacturer, they provide you with this all provide you with all these factors. Okay, and it's up to you what kind of noise you want to use. You can use white noise, colored noise, or Gaussian, non-Gaussian noise. So this way you simulate a sensor, a real life sensor by adding noise. And now once you have added the noise, then we move on to state estimation part. So here, what we do is like once we have the noises noisy sensor signals, we try to extract that required signal. Okay, so here I'm using a low pass filter to remove the high frequency noise and get the exact signal that I want. Now, once you get your signal, once you have your signal measured from your sensor data and state estimation block, you you provide it to a controller. Okay. Now here I've considered two type of controller. First one is your position controller and velocity controller. So let's say you have position signal as your feedback, then you can go for position controllers. And if you have your velocity signals as your if you can measure velocity signal, then you can go for velocity controller. So with velocity controllers, you have a good control over your acceleration, and the performance tends to be more better than your position controller. So yeah. So for control method, I've used a PID controller over here. So you have your reference velocity and filtered velocity. You have your reference velocity coming from the reference block and filtered velocity coming from filter block. So you compute the error and you use a PID controller to control the velocity. So apart from PID, you can use other control laws like model predictive controller and LCOR controller. Model predictive controller, it basically linearizes the model at each operating point and it computes the control parameters accordingly. So you get a superior performance. But the reason is the problem with MPCs, they are computationally very heavy, and it can be it can drain it can drain your battery power fast. But in case of then you have another controller, LQR controller. Now this controller is very good if you have power constraint on your system. Okay, and so I've linked some of the links for MPC controller and LQR controllers. So we saw how we can model the vehicle dynamics at various fidelity level, like according to the accuracy of the simulation desired. So we saw high fidelity hydrodynamic forces simulation and low fidelity hydrodynamic forces simulation. We saw how Aerospace Blockset can be used to simplify our approaches. Like we don't have to worry about choosing solvers, and we even don't have to worry about uh, calculating the relationship between reference frames and the body frames, the rotation matrices and translation matrices. We also took a look at how we can simulate sensors in real life conditions with noise using IME block. And we even took a look at some of the control approaches that can be used for an AUV. So So if I run this simulation, so here are the parameters. Okay. Now here I have three buttons. So we can simulate according to our requirements. So let's say I want to do low fidelity simulation and with system noise, and let's say I want to do velocity control. So update the diagram, and here are your X, Y, and Z thrust inputs from your controller. Now when I run it, yeah, so you can see it's simulating like fairly fast. Okay, and if I try to simulate it with yeah, with high fidelity simulation, it takes a bit to do the simulation.
So essentially, what we're trying to get at with this, we're talking about different fidelity levels, is that you don't always need a high fidelity simulation model to run your algorithms. So, for example, if you're testing your planning algorithm as opposed to your control, your actual low level controls algorithm, for the planning algorithm, you don't quite need such a high fidelity level in your simulation, just because you don't really care as much about the very accurate system dynamics. You're more looking at, is my AUV going from point A to point B? Is it activating its different modes as and when required? Whereas if you're designing a controller, for example, where you actually want, you really care about the system dynamics, you probably want to use a higher fidelity model in that case. And the trade-off is with simulation time, right? Just think about it. When you have a higher fidelity model, you're essentially solving a more complicated differential equation, whereas otherwise you can sort of dumb down the equation a little bit. It's still giving you an accurate enough answer, but it's saving you computation time. So you're not sitting at your computer watching the simulation run forever, right? So that's kind of the idea. You have to pick and choose what fidelity level you are comfortable with. Again, this is something that comes with practice, but as and when you do more and more of this stuff, you'll sort of realize what you're looking for from your system. So yeah.
So this is the trajectory that we have provided. This transitional reference block. So this is providing this trajectory. So yeah. So if you have some doubt, you can reach us at roboticsarena@mathwork.com, or we have a Facebook group. And if you want to post some questions, we have a good community over there. Similarly, you can check out our resources on MATLAB and Simulink Robotics and Arena. We have good resources on perception, robotics, implementation, and computer vision. So we provide we provide software licenses for RoboNation competitions, and you don't have, and these software licenses are free for the participants. I've attached a link here. Okay, you submit your you have to submit your software request form, and we'll take care of it accordingly. And we also have student launch blog. Yeah, you can find good you can find good resources related to controls and autonomous vehicles. And yes, it does include robots. So please check it out. So I'll yeah, that's the end of the session. If you have any question, you can ask me.
Thank you so much, Shubham. Like you mentioned, if you guys have any questions, feel free to pop them into the chat. Also, feel free to unmute yourself if you have a question. And they don't bite, so they've got some great answers for you.
Yeah, as I say every time, there are no stupid questions. So don't feel shy, just ask. Yes, Miguel.
Oh, yeah, go for it. You can unmute yourself if you'd like to ask a question.
Okay, so the question that Miguel has is the next step 3D animation? I think this is essentially 3D animation. It's just that you're not visualizing it, you know. You can definitely connect it to some sort of 3D visualizer, whether you choose. So if you're interested in the Mathworks products, then we've got something called Simulink 3D animation, which is our 3D animation software. We can also connect to the Unreal gaming engine. So if you want to get more photorealistic, photorealistic visuals of your AUV, you can use Unreal. We can also connect to Gazebo from Simulink and MATLAB. So you can. Those are some options that are available to you. Again, what that comes down to is a model fidelity, right? If I'm trying to build a controller, do I really care about what it looks like, or how I'm visualizing it? Probably not. That being said, you may want to do it. So again, it's one of those things where you have to sort of pick your poison, if you will, right? Depending on what you're doing, you can either visualize it in 3D or not. If you are using something like Gazebo, essentially what will happen, Shubham, maybe you can pull up that model again real quick, and I can sort of talk through that. Alicia, if that's okay with you.
This one?
The Simulink model that we just had open.
Okay.
Yeah, and so if can you go into that plant and environment model block?
Yeah.
And go into the dynamic solver. Right. So if you had to run this and visualize this in Gazebo, essentially what you're doing here is Simulink is computing so Simulink is this block, this 6 degree of freedom block, is solving the dynamics of the dynamic equations and all that kind of stuff. And what you can do, we have this feature called co-simulation with Gazebo or with Unreal or whatever other 3D visualizer you're interested in, VREP as well, if that's something that you're interested in. But essentially what Simulink will do is Simulink will compute, will at every time step solve that equation and output a set of state, state or state values of your AUV at that particular time. When you connect it to a 3D animation, you're essentially feeding those state values to Gazebo, and then Gazebo is just going to visualize it. So the visualization aspect of it is not particularly important when you're doing controls. Now, when you're doing, if you're trying to do something like autonomous navigation where you're connecting your perception system to your controller, yes, at that point it is important. So hopefully that answers your question, Miguel. Perfect. Okay. We have a second question from Bashir, who's wondering about how you can add other thruster configurations. That's a good question. Shom, can you go up a couple levels in the model to the thruster?
Yeah. So here. This one.
Yeah. If you go right there. So and can you click on that thrust direction? That little block there. So essentially this is what it's doing is we give it a thrust, and then we give it a location. So the location comes in when you're trying to compute your moments, right? So this is the orientation of the thruster. So 0, 0, and pi by 2, and then you have a rotation block that will basically convert it into whatever angle or whatever configuration you want to have it in. So can you go back up a level real quick? Yeah. And yeah, so pounds to new, and then the other way that we do it is we say, okay, so if you look at this, Shubham, can you highlight those mux signals after the transfer function? Yeah.
This one.
So essentially the way that is set up is you say, okay, position 1, position 2. So each of those 3 vectors is X, Y, and Z, right? So you feed that into whichever direction you want it to be fed into, and that's essentially how we do it. So we've done this. We've made a very simple assumption that all of the thrusters are on the axes, right? So x-axis, y-axis, and z-axis. Now you can essentially it's just a transform to move it around. So you can say, okay, it's not on the x-axis, it's a little further ahead of that, so that's going to introduce a moment, and then you just have to add that moment component to your simulation. So hopefully that answers your question. Awesome.
And Don, we will definitely be sharing this video online on YouTube, and then we're going to email it out to everybody that's registered for this evening's webinar, as well as getting it out later on social media. So you should get it tonight or tomorrow.
Can the slide deck be shared as well? Yes.
Yeah.
Yes, we will. So Don has a question. Can one thruster be enough to move it up and down? That's what simulation is for. You could put one on and see if it moves up and down, or you could put 2 on and see if it moves up or down quicker. It's, again, this is just this is for demo purposes. We picked this configuration. We just try to make it easy for ourselves. But simulation is a good way to figure out, to answer that exact question. Can one thruster move it up and down? Because what you do is you'd give it the weight of your vehicle and the density of the water that it's in, and then you can see, okay, with one thruster of, let's pick the Blue Robotics T200, right? That's their bigger thruster. You can put that on, see how fast it moves up and down, or you can change it at 2, see how fast it goes up. And so simulation is really good trying all these various configurations. So Miguel's question is, in your system, where is the polynomial trajectory? If you look at that reference block, so I've popped in a link to the GitHub repository where the code is. If you take a look at the, if you download that model and you take a look at the reference block, we're not giving it a polynomial trajectory. You could, the way our simulation works is we've essentially given it a timed thrust value. So we say, okay, for the first 5 seconds, fire on the thruster in the X direction, or fire on the thruster in the Z direction. Then for the next 4 or 5 seconds, fire on the thruster in the Y direction. So essentially that's how we're creating that trajectory. But you can just as well give it a trajectory. You have to use a position controller in that case, where you say, okay, essentially come up with some sort of a polynomial and break that into segments and say, okay, at every X number of seconds, try and get your vehicle to get to that particular position, right? And then it'll take it there. So that's what we mean by reference. In our case, again, this is a part of testing the simulation, because this is not a complete AUV, right? When you have a complete AUV, your reference path is coming from either your perception system or your or some sort of planning module, right? Whether you have a high level planning module that's saying, so for example, at RoboSub, if you have to go and do the challenge where you have to navigate through the gates, you're getting information from your perception system telling you where the gate is, and then a controller is saying, okay, I see the gate in front of me, solve that gate task, which means that, okay, you want to basically move in a straight line, right? So that all is going to come, that reference block is going to be replaced by that in your final system. And essentially what you want to do is, if you want to get a better model, you'll connect those two together, and you can do that in Simulink as well. So hopefully that answers your question, Miguel. I like these questions. It's a very chatty group.
Again, feel free, you can put your questions either in the chat, or if you'd like to unmute yourself and ask, you can do that as well.
So Miguel asked, where are we from? Shubham and I are both originally from India, but we live in Boston now, because that's where the Mathworks is based out of. Okay, next question. Can we control the linear velocity and rotational velocity simultaneously? I'd say yes. I mean, we've essentially in our controller, we're controlling X, Y, and Z individually. So your command would basically be, okay, you have to design a controller that can do that, right? So maybe you'd have to do some sort of a we've picked a very simple controller for this. It's just single input into X, Y, and Z. But you have to have some combination where it's almost kind of like a drone controller, in the sense that you sort of control two pieces of it, and then you're giving it two different values. Again, I'm sorry if I'm rambling. I'm trying to think about this on the fly. Shubham, do you have any, since you're the controls expert, do you have any suggestions on controlling rotational? And it's possible.
Yeah, it is possible. So
yeah,
here in this case, we are using a PID controller, okay? And when we map it to our thruster configurations, okay, so like the 5 thruster configuration, it will adjust the forces accordingly so that your velocity is maintained, okay? But if you want to directly access and control the velocity, then you go for other layer controllers like MPC and LQR, where you directly specify constraint on your rotational angles and all the cases. Now,
So hopefully that answers your question.
So when we convert it from PWM signals to the thrust values, right? When we have our X and Y, X, Y, and Z thrust values, when we convert them into PWM signals, and from that we determine the system model. Then according to thruster configuration, the PWM signals are distributed, and that's how they'll control the linear velocity and the rotational velocity in that case. And if you want, like, what do you say, the rotational velocity as a control, like as a control parameter, like X, Y, and Z, like X, Y, and Z are like we get X, Y, Z thrust values from your control module. So if you want rotational velocity in that case, then you go for LQR and MPC, where you can directly specify the constraints.
Yes, there are definitely better control schemes than what we've used. Again, it's just a dummy example for us,
Yeah.
The whatever controller y'all build will be a lot more complicated than this. It was more for the purpose of showing this demonstration.
And one thing here is like that what do we say, input for your reference rotational velocity will come from your planning module, the trajectory you provide. Okay, and that's when you can use that's when you can directly access your rotational velocity. Yeah, so Eric mentioned that he wants to discuss the questions. Yeah, you can. Okay.
So Don's question is, how did you get each transfer function of the thruster? If you really want to know how we did that, I'd recommend coming to the next webinar in the series when we're actually going to do a deep dive into that. But essentially the short 2-minute answer is we use a process called system identification. So what happens is we spoke to Blue Robotics and they gave us some data. So the data is essentially input and output. So we're given certain PWM input, what is the thrust output? Okay, so they've got a tank that they can measure all this stuff in, and they measure it and send us the data. And then we essentially, so system identification is a glorified curve fitting algorithm. It's just, there are different algorithms that work, but it's essentially a curve fitting algorithm. So you essentially take that input data, take the output data, try to fit the two together, and this system identification toolbox will spit out a transfer function for that, and that's what we used. But if you come to the next webinar session that we're doing with RoboNation, we're going to do a deep dive into that. So you probably want to come to that one.
Does anybody have any last minute questions? Well, thank you all for joining us tonight. Like both Shubham and Kalnel mentioned, you can email them with any questions that you have, but if you also want to reach out to us about anything RoboNation related, or if you have questions as well, we can forward them on. Please make sure to email autonomy@robonation.org. You can also visit our V-Bulletin to go onto our forum, and if you'd like to register for the next talk, which is going to be on May 19th, make sure you head over to robonation.org/community hour. You can get registered, and the links for both the previous session and this session will also be posted there as well. Thank you guys so much for joining us. Have a good night.